Okay, so this is a continuation of section 4.2, and in first theorem that we're going to prove in here, it is part of theorem 4.2. We actually proved the first three parts, A, B, and C, which amounted to saying that the congruence relation is an equivalence relation. In here, we could describe that these are properties to do with the behavior of the congruence relation with respect to addition, subtraction, and multiplication of of integers, or actually adding or subtracting two congruences. All right. So let's just start with the first one. So it says that if A is congruent to B mod M and C is congruent to D mod N, then their sum or difference remains congruent. Okay, so in other words, this is saying that congruence actually is preserved sort of addition. Even we can say a little more generally, that if you take a combination of the the two congruences, still we have this combination is congruent mod. Similarly, this works for multiplication. We can multiply. And even in particular, we're going to see that if I have A is congruent to B mod N, then I can multiply the two sides, or add or subtract to the two sides the same number, the same integer, then addition is preserved, and the same thing with multiplication. And we even take any positive power of the two sides of the congruence, and then actually this remains also valid. One other property is that if A is congruent to B mod M, then A is congruent to B mod any divisor D of M. All right? So we're going to go ahead and prove this. This is very, very straightforward. Just basically, we're going to be using the definition of congruence. All right? So let's just start with the first one. Actually, we can take the whole thing. Just need a little more space. All right, here's the proof. Utility. So I'm going to do this one actually for the addition, because the subtraction is actually very, very simple. All right. So we have A congruent to B mod M. This implies that M divides A minus B. And we also can write this as A minus B is equal M K for some K. And let's look at C congruent to D mod M. Again, this implies M divides C minus D. And this in turn implies that C minus D equals MK prime. Okay? So the K and K prime are in C. Well, let's add these up. All right? And for the case of subtraction, you just subtract them, basically. So you get A, all right, plus C. And we can then do the B minus D like this, so this becomes B plus D. And this is equal M, K plus K prime. And this simply means that M divides this difference, minus B plus D. And this exactly means A plus C is congruent to B plus C. Mod. The more general case is actually also follows from this. So I'm going to multiply the first equation by x and the second equation by y. So if I multiply, this is by x and this is by y, we're going to get ax minus bx is equal m times kx, and cy minus dy is equal m times k prime y. And again, when we add these, we come up with the ax plus cy minus bx plus dy. And this is equal m in kx plus k prime y. And once again, we conclude out of this that m divides this difference, and this is ax plus cy minus bx plus dy, and this means ax plus cy is congruent to bx plus dy. All right. Or actually, we could use also the one of the things that we're going to show later on to give another proof by multiplying this congruence by, the x and the y. That is using the part D, E, F, actually, we could do for E. This is a special case of this. All right. Let's move on to the product. All right. To show the product. So this time, instead of course, adding these, we're going to multiply. Let me start from scratch, actually. So we have these, all right? And actually, let me do slightly different even. All right, so from here, again, we get that A minus B equal mk. I want to solve for A in here, so this becomes B plus mk. And for this one, again, C minus D equal mk prime. And I want to solve for C. So this becomes D plus mk prime. Okay? Let me multiply these. Okay, so we're going to multiply AC. This is equal to B plus mk, then D plus mk prime. All right, so we fold this and we come up with BD plus BMK prime plus DMK plus M squared K prime. All right. Now, as you can see, we are getting actually BD in here. So if I take this to this side, to the left side, so we get this sum, each of its terms contains an M. So we could factor it out, and we have B K prime plus BK plus MK K prime. And this means that M divides, and we are done. Okay? So I'm just going to skip this. So this means that AC is congruent to BD mod. Alright, so this takes care of all parts of part D. Now let's move into a special case, which is E, where we have one congruence, and we wanted to show that if I add or subtract the C, then the congruence is present. So as you know, we have this. We also have C is congruent to C mod F, because M divides C minus D, which is equal to 0. All right, so therefore I can use D. We can add or subtract, and we are done. Similarly, we can multiply. So if you multiply these, you can get AC is congruent to BC mod M. So yes, this is true for both. Now let's look at the last part where we have actually not the last part. You see, F is for powers, okay? And as you can imagine, because the exponents are all natural numbers or positive integers, it looks like we could use math induction, okay? So F, so if A is congruent to B mod M, then A to the K is congruent to B to the K mod M for every K positive n. Okay, by induction, math induction on K. Of course, for K equal 1, the statement is true by assumption. And hold. So let's assume that we wanted to assume that A to the K is congruent B to the K mod M for some K bigger than or equal to 1. All right? Then I can multiply this by, from part E, implies that if I multiply the two sides by A, still the congruence holds, which means that A to the K plus 1 is congruent to, actually I want to multiply by AB, so, okay, sorry, not A in here and B, so I'm actually using part D more than C, okay, part D. All right, so we get here A to the K plus 1, and then this side we get BK on M. So if the statement is true for K, then it's true, that's what we're showing in here, it's true for K plus 1, so by math induction, statement is true for all K and Z. All right, the final one is part G. This is actually not part of the theorem in the book. So it's very nice and simple. So again, we have G. So we have A is congruent to B mod M. And we have a divisor of M. So let's see what each one of these implies. So this implies that M divides A minus B. And this in itself implies A minus B is equal to MK. This one implies that M equal DK prime. All right, so if I again substitute for, we take a B in here, if I substitute for this M, And in here, then I get A minus B is equal D K prime K. And now I can say, well, this means that A minus B, so D divides A minus B like this, because it is a multiple of D, and this in itself implies that A is congruent to B mod B. All right, so this is all straight. There's nothing very hard about it. In fact, we can do a little more, and that's something we will be using. Suppose we have a polynomial whose coefficients are integers. So here's another theorem. Actually, this theorem is proved in the next section. Actually, its natural place is here, so I'll put it in here. So let f of x equal an xn plus an minus 1, xn minus 1, and so on. A1x plus a sub 0 be a polynomial with integer coefficients. Integer coefficients. So all the AIs are integers. Okay? Or actually, it could be positive, negative. So this belongs to Z for every I. If it happens that A is congruent to B mod M, then f of A is congruent to f of B mod M. So in other words, if we evaluate the function or the polynomial at A and B, we get the values of this polynomial at A and B to be congruent. So this is numerical values in here. And the proof of this is actually more or less follows from the previous theorem. So we know that, here's the proof. A congruent to B mod M implies A to the K is congruent B to the K mod M for every K. And this time we're going to take it actually from, let's say, 1 up to N. All right, now, so we have this. Now, if I multiply this congruence by A sub I, all right, so you multiply by A sub I, A to the K, still congruent, this is by part E, A sub I, B to the K. For every AI, all right, which are the coefficient of the polynomial I between 0 and N. Because there are N plus 1 congruences in here, then I can actually add them up. So if I add these, I equal 0, all right, to N of AI. Of course, this is mod N here. Mod M for every these. So if I use the summation, means adding them all together, then we have also AI B to the K, K, I equal. Let me actually use in here A to the K instead of I, using the same index. All right, we use the same index. So this way, we multiply each term by the value, the x in here. All right, so let me put here a term using k. So let me use k, and k is equal 0 to n. This is k equals 0 to n. But this is nothing but the value of f at a is congruent to f of b mod. All right. One other thing is a corollary of this. Yeah, this will be useful, even very simple corollary in the future. And it says that if x equal a is a root or solution to the congruence equation, which is not very hard to know what the congruence equation is, okay? It means, some expression containing x and it's congruent to some value or some other expression in x mod m, all right? So the congruence equation is, let's say it is f of x congruent to 0 mod m. Okay? So if this is a solution for this congruence equation, means when you substitute for x by a, you get the two sides equality, where, of course, f of x as given in the theorem means it's a polynomial equation, okay? It's given in the previous theorem. Then the conclusion of this, for every b in z such that b is congruent to a mod m, b x equal b is a solution. Is a solution. So in other words, that's what this is saying, that it's saying that if a congruence equation has one solution, it has infinitely many solutions. And later on in this chapter, actually, in section 4, I think it's 3.4, we're going to be talking about specific type of congruence equation, linear ones. We're going to see that we're going to apply this to basically this corollary and see all those solutions. They are not going to be sort of different. They are going to be different up to mod m. Okay, so they are distinct. In other words, they are not mod m distinct, sort of. All right. Of course, this follows immediately from the theorem, because we have b is congruent to a mod m. By the theorem implies f of b is congruent to f of a. And f of a is congruent to 0 because it's a solution. All right, so it's a root, means it satisfies mod m, and which means that also b is a solution. Okay? All right, let's move on to actually other properties. Let me ask a question actually. congruence? Remember, congruence is like equation, like equality, sort in some sense. Okay? Question. We know that 50 is congruent to 20 mod 15, since 15 divides the difference, which is equal to 30. Now we know that two sides of this congruent are divisible, for example, by 10. Okay? So if I divide by 10, we get, of course, 5. The question is the congruence is preserved? Means that, I can divide the two sides by this 10, and like we do with the equalities, and we're going to sort of compare that with, is this canceling sort of, does it hold? Of course, the answer is no. So these are not congruent, because 15 does not divide 5 minus 2, okay? Which is equal to 2. All right? However, it turns out that if we're going to state actually a theorem that to tell us under what condition we can divide, or how we can actually sort of preserve this property that works for, for equality, for the relation, binary relation equal. All right? So it doesn't work flatly like this, but it needs modification. And this is the next theorem. All right? And here it is. Okay, so the theorem goes like this. Again, let A be congruent to B mod M. Actually, let me put it this way here, okay? So we have the usual A, B, C, D integers, and M is a positive integer. If AC is congruent to BC mod M, then A is congruent to B. Means we can divide by C mod, not M anymore, M divided by the greatest common divisor of M and C. All right? So this is the greatest common divisor of M and C. All right. And before we prove this theorem, let's revisit the example. So we have 50. We see is congruent to 20 mod 15. You know that the greatest common divisor of 50 and 20 is equal 5. So we can divide by the greatest common divisor in here. So we have then, this implies if I divide by 5, the congruence actually, as you know, these are actually multiple of 5, the 20 and 50, all right? But the mod in here is going to be 15 divided by 5. So in other words, just to kind of put it simply, if you want to divide two sides of a congruence, you can divide by the greatest common divisor of the two numbers, okay? And then you need to divide across the board, means the numbers as well as the mod. All right, now let's see if this is true. Of course, this one is 10, is congruent to 4 mod 3. Of course, this congruence relation actually does hold. All right. All right. Well, let's go ahead and prove this. So let's just start with the given congruence. Mod M. This implies that the AC minus BC is equal MK for some K in Z. All right. Now we can let's divide both sides since D, let me call this one actually the greatest common divisor. Let D equal greatest common divisor of M and C. All right. So this implies, of course, D divides M and D divides C. Okay. So I want to divide the two sides of this equation. All right, by D. And we can do this one because it has a C that D divides. So we're going to divide by D. So we get A, then we have C over D minus B, C over D. And this is congruent to, or equal to, actually still have equality here, equal to M over D K. All right, what does this mean? That which we can write as M K over D. All right, and or actually let me leave it like this. Let me leave it as a D here, and this still K. This implies that M over D divides this difference, okay, which is DC over, this is AC over D. Have AC over D minus BC over D. Which means that this is congruent to, okay, so this implies that AC over D minus BC over D is, or this one actually is congruent to each other, mod M over D. All right? Now we know that we can multiply this in it. All right, actually, let me track back. Let me go rearrange this equation. Let me write it here. So we have M over D. This divides AC over D minus BC over D. Let me write this one as actually C over D multiplied by A minus B. Okay, so we have this divisibility relation. So we have M over D, all right, actually divides C over D, then A minus B. Now we know that when we divide, all right, the greatest common divisor, of M over D and C over D, this is equal 1, right? We prove this property concerning the this one. So it means that these are relatively prime. So this implies that M over D and C over D are relatively prime. And from this divisibility, they cannot divide each other. So this means that M over D is going to divide A minus B. So from here, we conclude that the M over D actually divides the difference, because it cannot divide the factor in front. And this completes almost the proof. Just one more line in here, statement. Then we have from here, this implies A is congruent to B mod M over D. All right, an important corollary to this is the following. If A C is congruent to BC mod M, and the greatest common divisor of M and C is equal 1, which means they are relatively prime. Okay, so this is equivalent. M and C are relatively prime. Then we can just divide like we do with equalities. Then A is congruent to be mod M. All right? So you can just divide. So this only happens if this multiple C is actually not divisible, has nothing to do with the M. Greatest common divisor is equal to 1. All right. Another important result is concerning least common multiples. Okay, so we have greatest common divisor, sort of. Now let's look at properties with least common multiples. Here's another theorem. Again, let A, B is in Z, M sub I belongs to Z plus, these are positive integers, for I between 1 and up. We also have A is congruent to B mod M1. A is congruent to B mod M2, and so on. And A is congruent to B mod M sub I. So we have our congruences for A and B. Then A is congruent to B mod the least common multiple of the MI's. Okay, remember the symbol for least common multiple is a bracket, M1, M2, and so on. Okay, so this is actually the first part. Second part, in particular, if the MIs are relatively prime in pairs, or sometimes you call them pairwise relatively prime. What does this mean? This means that the greatest common divisor of any distinct ones, Mi, Mj, is equal 1 for every I does not equal to j between 1 and I. Okay? So if this is the case, then the A is congruent to B mod their product. Okay? M1, M2, up to M1. Okay. All right, let's look at the proof of this. So we're going to start by taking the standard prime factorization of the greatest common, the least common multiple. Okay, there is the proof. Let least common multiple M1, M2 up to MR equal I1 to R Bi alpha I, where Bi are primes and alpha I is bigger than or equal to. So this one is actually the prime factorization. This is the standard prime factorization of the least common multiple, M1 up to M1. Let's take one of these. This implies actually the P sub I alpha I is going to divide each one of these for every I between 1 and I. So remember, these alpha i's are the maximum, all right, of the primes that are coming from the primes that in the prime factorization of each one of these MIs, okay? So this is what these are. We've done it for, of course, 2 integers, but this is true for all. All right, now we also have, now since A is congruent to B mod each one of them, again for every I, then we have, this means this implies that Mi divides A minus B, again for each one of them. Now let's look at these two divisibilities, okay? So B alpha I divides Mi divides this. So this implies that Bi alpha I divides A minus B for every I. All right, and these are the actually the factors of the least common multiple. So this in itself implies that include out of this that the least common multiple M1 up to MR should divide A minus B. Okay? Because each of the prime factors actually divides that, and then the product of these prime factors must divide the A minus B. And this concludes the proof. So this means A is congruent to the mod M1 up to MR. In particular, once we have the these are relatively prime, okay, in pairs, then of course the greatest common divisor becomes the least common multiple becomes their product, right? We put this one in here. The second part, since greatest common divisor of Mi Mj is equal to 1 for every I does not equal to j. This implies the Mi Mj is equal Mi Mj. And the way we define actually the least common multiple for this, we define it actually recursively. Okay, so this, let me put R in here. So we define this as actually the least common multiple of, say, M1 up to M. This is R minus 1, okay, comma M sub R. Remember, this is actually it's going to be an integer, so we take the, whatever that is and to MR, and then we can, of course, take this farther and farther. So the end result, so this implies, because of this here, MR is equal to product. And this just actually follows from just the theorem itself. All right. The next thing I would like to do is to look at some applications of congruences. They could answer all kinds of questions, something you think of, something you don't think of. So I want to look at some of these. And we're going to do more of these applications throughout the other chapters. Here's a question. Let's suppose we want to find the remainder. Here's some applications. Of congruences. All right. So let's look at, we're going to be in form of examples, okay? So we're going to look at the first example. Say we're going to find the remainder obtained by dividing 3 to the power of 100 by this number, 101. Now, of course, there is a method which we can do is using total force, by calculating what this 3 to the power 100, or feed it into a computer, and then divide it by 101 and get the actual what the remainder is. Well, yeah, but we want to do it actually using more gentle or a simpler type of calculations. A regular calculator will help, of course, but we don't need a very sophisticated calculator or computer. The idea is we're going to use a technique which is called fast exponentiation. Or sometimes we call this one is successive squaring. All right. The idea is to take the number 100, and we're gonna write this as a sum of powers of 2. In the next section, we're going to be talking about this idea, which is actually what we call the binary representation of different natural or integers. So we know that 100, we can write it as a sum of actually powers of 2, which is going to be, we can write it as 64, which is a power of 2, we recognize it, and 32 plus 4, which is nothing but 2 to the power 6, all right, plus 2 to the power 5 plus 2 squared. So what I'm going to do, I'm going to actually calculate 3 to these different powers, all right, of 2. And we do this one by doing what we call successive squaring. And every time we do this, we're going to be reducing mod 101. So in other words, we don't want to carry the product to get very, very large. We don't want it to exceed. We don't want to actually exceed 101. All right? So here it is. We're going to starting with the 3 to the power of 2, well, or 2 squared, at least we need to have that. Because in this expansion we have 2 squared. So we're going to start with looking at, so in other words, let me say that. So we have this, we can write it as a 3 to the power 2 to the 6, all right? And this is 2 to the 5 plus 2 squared. And also we can write this as a product of 2 to the 6 multiplied 2 to the 5 and multiplied by 3 to squared. So if I can find each one of these, all right, and with not find it, but calculating that and reduce mod 101, then we can multiply them at the end and get what the actually the remainder will be. Because if this is congruent to whatever number is, then this number and that number we're going to leave the same remainder when divided by 101. So let's just start with the 3 squared, all right? Well, this is equal to 9, and this is, of course, we could think of it as congruent to 9 mod, or as it actually to 101. Then let's look at the square of this. Okay, so 3 squared. And this is going to give me 3 to the power 4. And which means we're going to square the 9. So this becomes 81. Okay, 9 squared is 81. And I'm going to just think of it as mod 101. Okay? It's going to actually think of this, and here I'm not saying actually congruent, this is equal to 9 mod, okay? we're using this computer science kind of notation. Then I'm going to take the 3 to the 16, which is nothing but to the 8. Sorry, 3 to the 8, which is a 3 to the 4 squared. Which means I'm going to be squaring 81 squared. All right? And when we get in here, it's going to be a number that is larger than 101. And I could reduce this to make it actually negative 4, for example. You can take reducing mod the smallest integer in absolute value. Okay? If you like, you could take a positive one as well, but this is very small. So when you go to the next one, which is 3 to the 16, this is, again, means a 3 to the 8 squared, and which means you're going to be squaring negative 4, so this becomes 16 mod 101. Then the next exponent is, which is a squaring, the 3 to the 16, it gives you the 32. 3 to the 16 is squared, but the 3 to the 16, it happens to be actually equal to 16 squared. And again, you can get this to be congruent to negative 47 mod 101. One more, which is a 3 to the 64, and this is the square of the 3 to the 16, 3 to the 32, sorry, squaring that. And when you reduce this, you come up with negative 30 mod 101. Alright, so we got all the pieces that we need in here, which is the this, and this. So let's look these up. We have the 32. Okay, so here's one of them. And we need this one. And we need the square to the 4. Okay, where's to the 4 is this one. Okay, now I'm going to put these in. So I can say this is congruent to 81 multiplied by negative 47 multiplied by negative 30. All right, mod 101. Even when we multiply these, we can also reduce mod 101. We don't have to multiply all of these numbers. Or as you see, the prior is not going to be very hard, so you could reduce it by subtracting multiples of 101. And at the very end, actually these together, you can replace this by, actually I don't have this one, I have these together. Give me a 5. And 81, again mod 101, and these give me what? Mod 101. So in other words, the remainder of dividing this very huge big number by 101, so this is the remainder. Okay. We look at another similar kind of calculations to this, and this one to show that Fermat's fifth number is in fact composite by proving that it is divisible by 641. Okay. So another example, show that if 5, which is equal to the 2 to the 5, plus 1 is divisible by 641. It means when we divide it by this number, it's not going to leave zero remainder. That's really what it is. So it is very, very simple. So the idea again is to take this exponent, very huge, all right, and divide it by 651, by the remainder of it, okay? So we have the 2, this is to the power, of course, 32. And I want to write the 30, well, 32 is, as you see, it's a power of 5, so all what we have to do is to start from 2 squared, and this is equal to 4. And you put this is mod 641. So we're going to do reduction mod 651. Then we're going to take 2 to the 4th, and this is actually 2 squared, which means we're going to just square the 4. And then we can take 2 to the 8th, which means squaring the 16. Now we are, I don't know, are we exceeding mod 641? If we exceed this, then we reduce, and let me do my calculation. Turns out this is actually, no, 256. So this is 256. 2 to the 8 is 256. All right, same one. Then let's look at the next one, 2 to the 16. That's going to be 256 squared. Now, this is going to exceed, and we need to reduce it. So it turns out it goes 154. Mod 641. Now we continue this, actually, till we get to 2 to the, which is the next one, actually. Well, 32 is 154 squared. And again, we need to reduce this, and it turns out this is actually is congruent to 640 mod 641. Then we finally write the F5, which is 2 to the power 32 plus 1, but the 2 to the power 32 is congruent to 640 plus 1 mod 641, which is congruent to 0 because it adds up to 241, and which a number is actually equal to the congruent. This is mod 641. Well, so yes, it means it divides because the remainder is equal to 0. Here's another example. All right. This is one of the examples in the book. And then if we need to find the remainder of a huge number when it is divided by 12. Okay? So the number is this, 1 factorial plus 2 factorial plus 3 factorial and so on up to 100 factorial. Even if you try, this is in your calculator, it's going to scream, all right? 100 factorial is very, very, very big number. So we need to find the remainder. Of dividing this number n equal by the 12, which basically we need to find, there's congruence mod 12. Now we use here a different technique, okay? We know that this 4 factorial which is equal to 4 times 3 times 2 times 1. So this is 24. And this is congruent to 0 mod 12. All right? Then if and now from 12 up to 100, all of these, they're gonna actually, in other words, if I add to this, okay, 4 factorial plus 5 factorial, because it's gonna actually contains the 4 factorial, each one of these, and all of these are congruent mod 12. So then all of these is congruent to 0 mod 12. And again, the reason for that is because each one of these actually divides, or it contains a 12. All right? So it has a 12 as a sort of a common factor. Well, now n is going to equal to 1 factorial plus 2 factorial plus 3 factorial plus all of this. Okay, 4 factorial up to 100 factorial. And this is congruent to the sum of these numbers is 1 plus 2, 2 factorial plus 6, okay, plus 0 mod 12. And now this adds up to 9 mod 12, and the remainder is going to be just 9. All right? Let me, one more question. I'm going to leave the details for you, just give you the idea. And this one to find, the digits in a big exponent, rather than raise it to a very big exponent. Okay? So here's another example. We need to find the last 2 digits. And you can modify this to 3 digits, 1 digit, and so on. The last 2 digits. And this is in decimal. Okay? Decimal digits, okay? Of this number. N is equal to 123 to the power of 456. Okay? Again, a very big number. Again, the idea is to try to find, this is equivalent. It's equivalent to find the remainder of dividing n by 100. Okay? So remember when we, by the division algorithm, okay, we have this. When we divide, we could express n as a cube times 100 plus r. All right? Where r, of course, bigger than or equal to 0, less than 100. So in other words, the remainder is going to be either 0 or it's a number that is going to be a 2-digit number, okay, or a one-digit number. It's going to depend. And once we do this congruence, then the remainder, when we're dividing by 100, so this is going to be, n is the multiple of 100 and whatever left, and then it's going to be actually the 2 digits, okay, the last 2 digits in the product. So the idea is now it's similar. So we're going to take the 456 and express this as powers of 2. So, okay, so you're going to take the exponent, all right, 456, and write it as sums of powers of 2, and the 10 log, this is 2 to the 8 plus 2 to the 7 plus 2 to the 6 plus 2 to the 10. And do the successive squaring, and after a little bit work, you're going to find that the last 2 digits, okay, of n is 61. So the remainder, when we divide n by 100, we get 61. All right? So I'm going to stop right here. So this is the end of section 4.2, and hopefully I will start working on the next section.